Hello everyone. So this video is the second part of how to create plugins for QAquifolium. So in the first part of the video, I went through how to create this the template essentially for this stormwater pond component. Now, as I mentioned in the first video, without having a connector for that works with the pond, I mean, we can still use it. Perhaps we may be able to use other types of connectors that can basically consider this or take this pond type um, as a essentially source to connect the pond to other types of maybe blocks. But it's basically what that takes is that we have to make sure that the connectors that we define are basically all the quantities that they need at their source are defined for this pond. Uh, for example, we may if you want to connect two, let's say, channel segments, the connector is going to need let's say Manning roughness coefficient. Uh, and that Manning roughness coefficient, we can of course define it for the connector, but we can also connect it for the blocks that are being connected using the connector, and which has some advantages if we do it that way. And so in that case, if you want to use that type of connector that is going to need the Manning roughness coefficient, it's not going to work with this stormwater pond, right? So basically here what we're going to do is we want to define a, a connector that specifically works with this pond. And for the sake of simplicity, I'm going to define this connector to act as a weir, based on basically a rating curve that can be adjusted by the user during the runtime. So now, if you look at the basically the JSON file that we created in part one of this video, you could see this hierarchical kind of structure. So the first level, essentially after this, we open the bracket for the root, if you want the root branch, is where we define our the name of our objects, and then we have a second level when we essentially define all the properties of the template pond that we defined here, and then in the third level we if needed we can designate or we can assign properties to those properties, or we can use a different name for those properties. Let's say some quantities or some characteristics to those quantities. So for example, they have storage. The storage has some variables that define how this storage property to behave and what it is and how it's basically received from the user and so on. So there's this hierarchical structure. So if I want to define a new component, it's going to be at this level, right? So basically what I'm going to do is I'm going to go to the end of this, the root branch, and I need to add a comma, of course, if I want to add a new item or a new branch. And then the branch, let's call it where, right? So then here I'm going to define the variables of this where, right? So now as we did in part one, there are a few things that I need to define here. So the first one is I'm going to say, let's do the indentation correctly. Okay, so I'm going to go here. I'm going to go one step forward. So we have type. So this says what's the type of this component, and we know it's a link, right? So this is going to be a link, which is going to connect two blocks. And then the next one, we have type category. So we talked about type category in part one. So the type category for this one is going to be link. I'm sorry, it's going to be connectors. Okay, and what that is basically if I um, start QAquifolium, what you're going to see is you have blocks and you have connectors, and we want all the connectors that we create to go under connectors. You can have other things too, other kind of categories that are basically user defined. I'm going to stick to the ones that are provided in the default template. Okay, so I'm going to move this away. Oops. Okay, let me bring back my. Okay, so so then the next item that we can define, it's actually optional, but it's good to have it, is description. So we can have a description where we kind of in more detail explain what this this component is. So what we can say here is, let's say it's a V-notch where um, so let's say, I don't know, based on a power law rating curve, right? And so we can have other types of wares. Of course, if I want to define a different type of ware, the name has to be different, right? So anyways, then we have the icon, right? So we can have an icon for this one. And the icon, the way we define it is we have a block underneath, right? And we just provide the file name, and the file name is, as I said, I have these icons stored in my the folder that I created. So the folder was, I guess, stormwater pond instructional video. And what I have is I have an icon for a V-notch ware that I created myself. So let's get the properties of this. So we can just simply copy paste the address. So I'm going to copy it here, and then go back and then paste it, and then of course the name. So you can copy the name as well. So the name is V-notch ware. Okay, let's put it here. .png. Okay, so that takes care of the icon. Now I'm gonna do it because in part one I explained some some major kind of properties that all the components should have. I'm just gonna copy paste. For example, we need a name, so every component that we define is going to have a name, and that's where the name of the object that we create through the graphical user interface is essentially saved, right? So I'm going to just copy and paste the name, and the structure of the name property is going to be the same no matter what component we are defining. Okay, so that's and then we have a bunch of other properties that all components have, which are just is default, and I'm just going to copy and paste them from another file that I have. I can copy and paste them from the pond, the stormwater, the pond that we just created earlier. So just copy. Oh, I'm sorry. Oh, I'm sorry. Actually, since this is uh, a link, we don't have an x and y and width and length. So my apologies. We don't need those. One thing that we can assign here is a color. So it's a color that when we draw the links, they can be color coded, so that it's easier for them to be identified. So I'm going to just add, and the way color works is essentially by, so the structure is like that. So basically it's a quantity is color, and then so I think I've lost track of my brackets, but no, but I think it's fine. So basically it's a string type, and then the way we put is that we actually enter the colors basically based on the RGB values, red, green, blue. So this one is going to be kind of light. I think this is going to turn out to be light blue or cyan color, and we don't, basically this is, we want to assign a default, and we don't want to allow the user to change the color during the runtime. So every time we create a where, it's going to have the same color. Now let's go to the kind of properties define the governing equations. So basically what we want to do is that we want basically a power law to control the flow out of our pond, or flow through the where. And so let me go here, minimize this one and this one for now. So basically this is the type of equation that I want to use to determine the flow out of basically through the where, no matter what the where is connected to. And basically, so the flow rate is equal to a coefficient times the hydraulic head of essentially the source, or what we are connecting the where to, minus basically this is a crest elevation. Of course, you have the where has a crest elevation to the power beta. Now, something that I want you to keep in mind is that the value of whenever h is smaller than z0, so the hydraulic head in our pond is lower than the crest elevation, we don't want any flow. So basically we have to apply some sort of a function here to make sure that the flow is going to be 0 as long as our hydraulic head is below the crest elevation, right? So and we use this function called POS, basically POS, in order to perform that. So let me bring back my template file. So this is what we have. And now, in order to do this, basically I first have to define some variables, including the crest elevation, the alpha coefficient, and the beta coefficient, right? So for the crest elevation, so let's just add this property called crest elevation. And now what we're going to do is so what are the properties of first of all, the crest elevation is a value that we enter, so its type is going to be a value, and it's let's do a description, right? So description is going to be let's say crest elevation, and then we want the user to provide this, so we're going to make ask user true. Then the delegate is going to be a unit box. Okay, I think I have some sort of a mistake here. Okay, which I can correct it. Then and then I want to allow this. I mean, even though probably not very applicable, but I want to allow the users to treat the crest elevation as a parameter to be, determined through some sort of inverse modeling, including, for example, optimization. We may have, I don't know, we want to design a stormwater pond, and our question may be, okay, what's the best elevation to place the where. Okay, so we can actually treat this as a parameter to be estimated, and I'm going to close that. And the rest of them I'm going to go through kind of quickly because these are um, okay. These are pretty repetitive. So we have these properties alpha and beta, which I'm going to copy and paste from a file that I previously created. So this is our alpha parameter, and then we have a beta exponent. Okay, so basically what we have here is alpha and beta are both values. We have some description, which is a coefficient alpha in this rating curve, and h here is basically our, let's say, I don't know, you may want to do this, minus z0, for example, or something like that. So basically this is the equation that we're going to use for calculation of the flow. So this is just a description that's going to be shown in the property box, and then the rest of the values. And then I want to also add this criteria to make sure that alpha is always greater than 0. If not, the user is going to receive an error saying that alpha must be positive, and this value is not going to be accepted. Same thing with beta. So as you can see, we have everything is pretty much similar to alpha. These are just two parameters that are going to be received during the runtime. Now we are ready to do the flow, basically to define what the flow rate means. Now, something that I want you to remind you is, if you remember what we did in the part 1 of this video, was when we defined the storage, I mentioned somewhere that flow is flow. So the flow that determines the balance equation is, we defined it as flow. So now what we want is every connector that I'm going to define is going to have this flow properties that's going to be dynamically calculated, and when we connect the connector to a pond, for example, it's going to look for basically when we want to do the water balance in the pond, it's going to look for the variable flow of all the connectors that are connected to it, and then based on that, it's going to do the water balance, right? So now what we're going to have is that we're going to have a flow property, and so the type of this flow property, let me close this bracket. It's always a good idea to, when we open a bracket, close it at the same time, because it, to make sure that our brackets are all balanced out. So basically the type of this is, the flow is going to be calculated based on an expression, right? So basically the type of the flow quantity is an expression. Okay, and then let's say description is going to be flow rate. Now keep in mind that the units should not really matter as long as we are consistent with the units. And the default time units in QAquifolium is days, right? So, but if you want to, for example, if we want to enter the alpha and beta values so that they give us the flow in, for example, cubic meters per second or in CFS, then we can do a unit conversion right here. When we're writing our basically our expression, we can just do the unit conversion to convert them to, for example, another unit that is commonly used in QAquifolium, for example, maybe cubic meters per day. But I'm not going to do it at this time, assuming that all the units that are going to be applied are going to be essentially consistent. So now I want to write the expression. So this is our expression. So I'm going to just type the expression the way it is, with one exception. So basically we have alpha, right? So that was our equation. So let me go back and have a look at our equation. So we have alpha h minus z0 to the power beta. So that's easy. The only thing is that we're going to need a head, right? Now the head is the head of the block that we're going to connect using this connector where, right? So I'm going to put a dot s And the dot S says that whenever you want to look at the head, go and look at the head from the block that is being connected. Because of course here, for the connector, we're not going to have, we don't have a head variable, right? We only have it for the stormwater pond that we're going to connect using this connector. So it's going to be head dot S, and then minus, of course, we have this crest elevation to the power is going to be beta, right? Now, one thing I need to pay attention to, I don't want this value to be, I mean, if this the head of the source block minus crest elevation is negative, you're going to be in trouble, right? So what I'm going to do is that I'm going to add this function. It says underscore pause, right? So what that says is that only return the value of this quantity inside the parentheses if the value is positive. If it's negative, make it 0, right? And that's exactly what we want, right? So okay, what else? We want to include this flow. Of course, we want to include it in output. Include in output is going to be true. We want to be able to see the values of the flow that is calculated dynamically through the simulation after we run the simulation, right? And now one additional thing I want to add that's very important. So I'm going to add this, there's this keyword called apply limit, and then I'm going to make it true. So what that is we may have a situation where our stormwater pond is completely empty, right? So that the storage inside our stormwater pond is 0, and we have an outflow, and the value of the outflow, it doesn't happen in this case, but there may be, you may imagine a case when the value of outflow is not necessarily 0 when the storage is 0, and that will make our storage to go negative, right? And we want to prevent that. So whenever I switch this apply limit keyword to be true, what that means that whenever the storage in our or whatever variable that is being transported through this flow, whenever the value is 0, shut this flow off, right? And that's very important in this case. So then and of course this is not, we don't want to ask, the flow is kind of dynamically calculated, so we don't want to ask it from the user. So that's pretty much it. This is how we define the where. Now what I'm going to do next is I'm just going to try it, build a model using this. I'm going to save this, and I'm going to go and open QAquifolium and try to load this plugin and see if I can do some simulation. Okay, so now I'm going to run QAquifolium. So here you got it. Let me make the window a little bigger. And so the first thing, let's just add the plugin that we just created. So I'm going to go to preferences, and I'm going to add a plugin where we saved it. So we saved it here. So we have this pond plugin.json. So now we have these two components added. Basically, we have a stormwater pond, which is a block, and then we have a V-notch where based on a power law rating curve. So that's exactly the description that we put in. And so what I'm going to do is basically I need, in order to use the connector, I'm going to need 2 blocks. I can use for the receiving essentially block. I can probably use, I have a variety of options because we are not going to use any quantity of the receiving block. But I'm going to use a pond. I'm going to use 2 ponds, and I'll let water to go from one pond to another one. So I'm going to add this pond right here, and let's do the other one too. So this is going to be our second pond, which I'm going to place here, and then let's just assign some of the properties of the pond. So I'm going to do the initial storage. Let's say there's 100 cubic meters of water initially in pond 1. The coefficient, let's go with a 5. And the bottom elevation, let's say that's 10, right? So the second one, I'm going to assign the numbers to the second one because there are some criteria, so I can't really leave alpha and so on empty. So I'm going to say, I'm going to use the same number. So the coefficient alpha is going to be 5, and initial storage really doesn't matter. I'm going to leave it at 0, and that's pretty much it. You know what? At this time, I can actually run the model to get an idea about what the head will be in pond 1, so that when I'm assigning the uh, crest elevation of the weir, I'm gonna assign it so that I'll definitely get a flow. So let's just run this. So this is run again. No dynamic. I don't expect anything to change with time because we don't have the connector. So I'm gonna just look here and look at the hydraulic head, and I'll see that just like part 1, we get a head of around 14.47, something like that, and that's enough for us. So then I'm gonna add the weir. So the weir is gonna go from here to here, and then let's assign some of the properties of the weir. So the coefficient, I'm gonna go with a large number. The exponent, I'm gonna keep it at 2.5, which is the number of it's actually for V-notch, whereas we know that that's the empirical value. And the crest elevation, I'm gonna go with I'm gonna go with a number that is smaller than the 14.47 that we got for the head. So I'm gonna go with, let's say, 13, right? And that's pretty much it. We set up the system. Let me go ahead and save this. I'm gonna save it as I'm gonna pond weir system.script. So I'm gonna replace that because I already had a file with the same name. And now I think it's ready. The model is ready to be run, so I'm going to run it. Done. And now I can look at different things. So first, let's, for example, look at the flow. So if I look at the flow, this is what I'm going to see. I'll have something like 100 and something, and then it's reduced to, maybe, I don't know, 10 or something. And then I can also look at, let's say, the storage in pond 1, which is declining. I can look at the water depth. Let's say the water depth is, as expected, declining, but it's not going below, as we expect, it's not going to below 3. And that's it. And we see that the water is accumulating in the receiving pond. So that was it for this lesson. Have a good day.